Picture a square with 4 sides laid out in 2 dimensions. Now take the corners and extend lines going perpendicular to the square, piercing into the 3rd dimension and forming a cube. Now take each of the 8 corners and extend a new line from each of them, this time piercing into the 4th dimension, perpendicular to every existing line in the cube. This is a hypercube, also known as a tesseract. Higher dimensional objects are almost impossible to envision in your mind's eye, but, if you can, scientists in mid-19th century England believed great rewards would come your way. For many Victorians of the time, the 4th dimension represented the realm of the spiritual, the font of divinity. It had started in science with mathematicians like Bernhard Riemann, who had just devised a new kind of extra-dimensional geometry beyond that of Euclid, opening up our understanding of spaces, forms, and structures beyond the triangles of 180 degrees and parallel lines we had known before. And from there, the fertile Victorian imagination turned the 4th dimension into an almost magical realm where we could find commune and connection. But for H.P. Lovecraft, a New England author born towards the end of the century, within the higher dimensions of the universe he found only horror. In one of his tales, The Dreams in the Witch House, Walter Gilman, a student of physics and mathematics, finds that the room he is renting has bizarre dimensions. Dreams come to him every night, drawing him deeper into higher dimensional planes filled with gods and monsters. This Lovecraftian fear is fundamental and inescapable. It is a fear of the unknown, a fear of the true scale of the wide universe, and what lies beyond. And yet some of us are brave, or, at least, foolish. Some scientists have peered into the depths of the cosmos, seeking the darkness of these hidden dimensions. For it appears that a century after Lovecraft wrote about their horrors, we now think that there is possibly some truth to these ideas, but not quite in the way he proposed. It turns out, yes, we may need to look to extra, higher dimensions for answers on the true nature of the cosmos, but from a lower viewpoint than we had originally thought. Our entire universe may be nothing more than a thin, 2-dimensional membrane. The answer to matter, gravity, and even space-time itself may lie in the reduction of dimensions. Einstein was not a slow starter. Documents show he was actually a child prodigy, excelling in physics. This was helped by being surrounded by electricity and magnetism in his youth. The Einstein Company, run by his father and uncle, manufactured electrical equipment. Encountering science at a young age was clearly a huge help in his later discoveries. His story is a reminder of just how powerful early curiosity can be, and nurturing that spark is exactly what KiwiCo aims to do. KiwiCo offers monthly hands-on projects designed for every age and interest, from toddlers exploring the world for the first time to teens, and even adults, tackling advanced science, engineering, and art projects. My producer and his family had a great time with their crate from the Kiwi Crate subscription line, a monthly delivery for kids ages 6, 9. They got to build their own planetarium, mix and match constellations, design star patterns, and even see how the Earth and Moon orbit the Sun. The kids loved the excitement of opening the box, and since the projects and elements are reusable, they've been able to explore them again and again. Their family is already counting down the days until their next monthly delivery. If you'd like to spark that same excitement and inspire the little scientists and engineers in your life, use my code HISTORYOFTHEUNIVERSE for 50% off your first monthly KiwiCo crate, or head to kiwico.com/historyoftheuniverse. Possibly Gilman ought not to have studied so hard. Non-Euclidean calculus and quantum physics are enough to stretch any brain, and when one mixes them with folklore and tries to trace a strange background of multi-dimensional reality behind the ghoulish hints of the Gothic tales and the wild whispers of the chimney corner, one can hardly expect to be wholly free from mental tension. Like Walter Gilman's exploration of his rented room, the journey to higher and lower dimensional answers is a strange one, and it starts in the most unlikely of places, not in studies of the quantum nature of reality or into the edge of the universe, but in an attempt to make more efficient steam engines. Death is nothing, but to live defeated and inglorious is to die daily. On the 15th of October 1815, Napoleon, once the Emperor of France and master of half of Europe, stepped foot onto his new domain, the tiny island of St. Helena, his second exile and final prison from where he would never return. It is said that during his final years on the rock he insisted that the men who served him wear military clothing and the women evening gowns, his defeat at Waterloo months before hard to swallow, but it was final. Never again would he seize glory, never again would he march in triumph. What he left behind was a fragile monarchy restored in France, a regime that did not take kindly to any friends and associates of the exiled emperor. and that included a young Sadi Carnot, an engineering officer of the French army. Born in 1796, Sadi was the son of Lazare Carnot, the brilliant mathematician and commander of the French Revolutionary Army, and one of the few who successfully navigated the turmoil of the rise of Napoleon. But Sadi would have no such luck. He maintained his position in the military, but was frequently passed over for promotion due to his family's connections to the exiled emperor. Eventually, he took a pay cut to secure what was essentially a sham position, but one that allowed him to spend his time focusing on his intellectual curiosities that would change our entire understanding of how reality works. In 1824, Carnot published his greatest work. Believing that one of the causes of the French defeat was the inefficiencies of their engines, he sought to mathematically describe the perfect engine in an essay entitled Reflections on the Motive Power of Fire. Dying in 1832, however, his treatise never got the recognition it deserved in his lifetime. But it would turn out that Carnot had unwittingly stumbled upon the building blocks of an entirely new kind of physics. Decades later, his book would catch the attention of Rudolf Clausius, a German physicist and mathematician. Something in Carnot's work fired his ingenious imagination, and in 1850, Clausius would state what would eventually become known as the second law of thermodynamics, that heat does not spontaneously move from a colder body to a warmer one. He had no idea what he had unleashed upon the world. In 1888, however, he too would pass away, handing the torch of exploration to new scientists and new revelations, and leaving it to them to uncover the dark mysteries and bizarre consequences of what he had discovered. At its core, thermodynamics rests on three basic laws we assume to be true because we always observe them to be true in nature, and the entire rest of thermodynamic theory grows and expands from that foundation. The first law of thermodynamics is a version of conservation of energy. Energy cannot be created or destroyed, only transformed. The second law, first observed by Rudolf Clausius, states that entropy never decreases. This means, among many other things, that heat does not spontaneously move from a colder body to a warmer one. The third and final law states that a system's entropy approaches a constant as it cools towards absolute zero, implying that it is impossible for any system to ever actually reach that point. And so central to the second and third laws was this new concept of entropy. Prior to the work of Clausius, scientists going back to Newton believed that heat was some kind of particle that traveled from one object to another. But Clausius disagreed. While energy could not be created or destroyed, not all energy was usable. For example, when a piston is driving a motor, some of the energy is gainfully used to create movement while some of the energy is lost to friction. When a fire is used to cook food, some of that energy is lost in light and excess heat. Therefore, Clausius reasoned, heat itself could be transformed, and we needed to keep track of the useful and useless kinds of heat. He dubbed this non-usable form of heat entropy. And so the three laws of thermodynamics obviously worked. They explained experiments and made powerful predictions, but in a sense they were created out of whole cloth. Where did they come from? And so what did this mean? What were the underlying connections between temperature, work, entropy, and everything else? As the first generation of pioneers like Carnot and Clausius passed, it would become the job of the second generation of explorers to understand the unfolding mathematical world that they created. And it was they who would find much deeper connections to the true nature of reality than they could ever have expected. It must be splendid to command millions of people in great national ventures, to lead 100,000 to victory in battle, but it seems to me greater still to discover fundamental truths in a very modest room with very modest means, truths that will still be foundations of human knowledge when the memory of these battles is painstakingly preserved only in the archives of the historian. The exploration of this new science of thermodynamics would come to bear the greatest on Ludwig Boltzmann, an Austrian physicist born in 1844, more than a decade after the death of Carnot, and more than 20 years after Napoleon finally passed into the archives of history on St. Helena. For Boltzmann, a truly modern scientist, there was something deeper happening in the three laws, and he suspected it had something to do with the microscopic nature of materials. At the time, scientists around the world were just beginning to recognize and classify the elements of nature, like hydrogen and oxygen, and understand their properties. However, while most scientists had a sense that these elements were made of some fundamental unit, the atom, they hadn't yet proved it. There was still debate as Boltzmann's genius and bravery was to unite the burgeoning theory of the atom with the laws of thermodynamics. He envisioned gases and fluids as composed of countless tiny particles, and sought to understand how those particles interacted and behaved, hoping that those deeper interactions would naturally give rise to the large-scale thermodynamic properties that earlier scientists had recognized. He would be proven right, and his revelations started with entropy. In 1877, Boltzmann created a new definition of entropy, this one based on the behaviors of countless microscopic particles within the whole, rather than a single uniform mass. His definition of entropy relies on counting the number of possible arrangements of tiny particles that can lead to the same observable large-scale property. To help understand this, let's imagine you finally get around to cleaning your kitchen. You clean all the dishes and put them away in the cupboard. You take out the trash and recycling. You throw out all the moldy food from the fridge. You even clean the gunk out of the grout behind the sink. After hours of effort, you stand back to admire your handiwork. The kitchen is spotless. There's a place for everything and everything is in its place. Boltzmann would say that this is a state of very low entropy. You have the property you can measure, which is cleanliness. And for the kitchen to give you that property, there is one and only one way that everything can be arranged to make it clean. In Boltzmann's language, there is only one microstate of kitchen perfection that leads to the macrostate of cleanliness. Fast forward one day. You live your life. You make dinner, you clean up, you open up the fridge for a midnight snack. In less than 24 hours your kitchen is noticeably less clean. Boltzmann would say that your kitchen now has a higher entropy state. Your kitchen is slightly dirty, that is the observable macrostate. And there are many ways to make your kitchen give you that observable property. Maybe there's glass left in the sink. Maybe there's a bit of crumb in the corner of the counter. Maybe your cup left a ring on the table. And so on. All it takes is one little thing to be wrong, but there are so many options of what that one little thing could be. There are many more ways to be untidy than tidy. This is how we arrive at our connection between entropy and disorder. Strictly, entropy is a measure of the number of microstates that lead to a specific observable thermodynamic state, like pressure and temperature. But also, the higher entropy a system has, the more microstates it has available, the more disorder it has. This realization, this powerful connection between the possible arrangements of microscopic particles and one of the key concepts behind the laws of thermodynamics, birthed yet another new branch of physics, known as statistical mechanics. We now understand all of thermodynamics to arise out of statistical mechanics, especially once the existence of atoms was demonstrably proven by Einstein in 1905. What we call temperature in a gas, for example, is the average kinetic energy of the particles of the system. Hotter temperatures mean greater kinetic energy, which translates as all the particles of air moving around with greater speeds. Thus, when we immerse our hands in a hot gas, all those particles slam into our skin, imparting their energy on us, transferring heat in the process. The key to statistical mechanics is that we don't have to know all the properties of all microscopic particles making up the system. We don't have to keep track of every single air molecule with its detailed position and momentum to arrive at an understanding of temperature. Instead, we only have to apply probabilities. Hence the statistics in statistical mechanics like counting microstates or computing averages. But obviously these 19th century explorers behind thermodynamics and statistical mechanics were not yet opening doors to new dimensions. Instead, they were developing a basic mathematical toolkit. Any object with heat could now be described by entropy, and entropy could be described in terms of microscopic motions. However, in the coming decades, these tools would be used in the most unexpected places. The most unlikely objects to possibly have heat, black holes. And in the explorations of black hole thermodynamics, the first hints would emerge that something was very wrong with the universe. The dreams were wholly beyond the pale of sanity. He had been thinking too much about the vague regions which his formulae told him must lie beyond the 3 dimensions we know. As Lovecraft's story continues, Walter Gilman's dreams take him to a bizarre otherworld. A place he believes to be higher dimensional, full of abysses whose material and gravitational properties and whose relation to his own entity he could not even begin to explain. Lovecraft continues, the abysses were by no means vacant, being crowded with indescribably angled masses of alien-hued substance. Everything he saw was unspeakably menacing and horrible. Luckily, in our journey to the most extreme place in the universe, the logical endpoint of the study of thermodynamics, we will have a guide to help us. A guide with plenty of experience dealing with impossible demons, I look upon the world as a product of God. Jacob Bekenstein was a devoutly religious man, and yet the pioneering scientist did not see this a barrier to his explorations of the extreme places of the universe, a tightrope that many physicists both before and after him have walked. Indeed, Newton himself was a devout Christian, and more recently Georges Lemaitre, father of the Big Bang, was a Catholic priest. Bekenstein delighted in unfolding the mysteries that God had left him, and saw studying the universe's inner workings as a form of worship. The more we learned about nature, he believed, the closer we came to knowing God. And yet the most famous of these explorations in the early 1970s would take him to the brink of something far more demonic than holy, arguably the most powerful source of ruin in the universe: black holes. There is no known greater monster in the universe than black holes, no grander destructive power. Nothing can survive an encounter with them, not planets, not stars, sometimes even galaxies wilt in their presence. And of course, at first glance, they have nothing whatsoever to do with thermodynamics, statistical mechanics, or the extra or hidden dimensions of the universe. First found buried in the mathematics of Einstein's general theory of relativity, they are, in the words of Nobel Prize-winning physicist Subrahmanyan Chandrasekhar, the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time. But despite this perfection, in many ways black holes created more headaches for scientists than they solved, in particular in regards to two grand mysteries, both tied to their fundamental nature. First, the singularity within, the point of infinite density at their centers as predicted by general relativity. Infinite densities cannot exist, and so their appearance was a clear sign that general relativity is not complete, that there is a more fundamental theory that has to be used to explain what really goes on. But unfortunately for us, singularities are forever inaccessible, because they are locked away behind the one-way barrier of the black hole event horizon. You can travel beyond the event horizon if you dare, but like one of Lovecraft's unfortunate adventurers, you will never be able to reveal your findings to the outside universe. And it is these event horizons that present the other mystery. Black holes are the only places in the entire universe where you can enter but cannot leave, and so it left theorists questioning what this means. Are event horizons truly what they appear to be, roads of no return, or is there more to the story? These were the kinds of questions that drove Bekenstein. The singularities were a massive unsolved problem, yes, but it seemed to him that the event horizons were just as mysterious, and they had the added bonus of actually being observable to the outside universe. And so, by 1973, Bekenstein had discovered something uniquely strange about his pet demons. Despite their fearsome reputations, black holes are almost absurdly simple. From the outside, black holes only present three quantifiable properties: their mass, their electric charge, and their spin, or angular momentum. Regardless of what goes into them, whatever stars and gas and molecules, whatever planets and moons and comets, whatever man, woman, or child, all the information gets neatly tucked away from prying eyes behind the event horizon. All that we ever get to see is those three simple properties. If you constructed two black holes from two very different sources, say, one from a collection of stars and nebulae and the other from just information, for example, an incredibly long number. If those black holes had the same mass, charge, and spin, you would not be able to tell them apart. Bekenstein would go on to call this idea the no-hair theorem. In essence, the idea that black holes are bald of information. His mentor and advisor, John Wheeler, found the phrase delightful famous physicist Richard Feynman thought it obscene. But despite Feynman's objections, the phrase stuck. The baldness of black holes led some theorists to suppose that black holes are regions of zero entropy, places of no information. But Bekenstein quickly realized that the opposite was true. Black holes could not be regions of zero entropy. It would mean that you could toss materials into black holes and destroy their information content, something completely forbidden in quantum mechanics. So Bekenstein realized that black holes must have an entropy associated with them, but how much? He proposed that black hole entropy is proportional to their surface areas, that is, the size of the event horizon. The larger the black hole, the more surface area it had, the more entropy it contained in its volume. And it was this that led Bekenstein to make perhaps the most bizarre statement ever made about black holes, which, considering how bizarre black holes already are, was quite the achievement. He proposed what would become known as the second law of black hole thermodynamics, that black hole surface areas never shrink, that event horizons never get smaller. This was in analogy to the second law of thermodynamics, which states that entropy never shrinks in a closed system. And since Bekenstein guessed that black hole surface areas were proportional to their entropy, this new kind of second law popped right out as an immediate consequence. At the time, this was only a conjecture, an educated guess as to an intriguing property of these mysterious creatures. A bold guess, true, but still a guess. And then came Stephen Hawking. Hawking, unlike Bekenstein, was not a religious man. God is the name people give to the reason we are here, he said. But I think that reason is the laws of physics rather than someone with whom one can have a personal relationship. And yet, there is no record of any clash, or this being the source of any tension between the two men. No, to begin with, Hawking's qualms were solely with Bekenstein's physics, believing that whilst his work on black holes was intriguing and possibly profound, it was riddled with errors. Hawking argued that black holes could not possibly have an entropy associated with them because they did not radiate, they did not produce heat, and so we couldn't use those familiar thermodynamic terms to describe them. And so Hawking set out to prove Bekenstein wrong, and in the course of his work, found that his rival was exactly right. By carefully following the evolution of the event horizon since the moment of a black hole's inception, Hawking discovered that the one-way boundary interacted in strange and unexpected ways with the surrounding spacetime. Through a quirk in quantum mechanics, particles could escape. Black holes were not black. They emitted, ever so slowly, a tiny amount of radiation. Hawking's result, published in 1974, was a bombshell. Long had physicists suspected that there was more to black holes. But nobody expected this. Black holes emitted radiation, later named Hawking radiation, with smaller black holes emitting more than larger ones. And that was not all. For the discovery of Hawking radiation, along with Bekenstein's original insights into the nature of black hole entropy, created perhaps the greatest paradox of modern science, the black hole information paradox. To begin with, Bekenstein's second law of black hole thermodynamics was ruled out. Black hole surface areas do not always grow. Instead, if left to their own devices, they shrink as Hawking radiation saps mass from the black hole. But Bekenstein had correctly discovered that black holes do have an entropy. If black holes did not radiate, this would not be a problem. Information is not destroyed, it's simply hidden from view for all eternity. Frustrating, but not a problem for our understanding of the universe. But black holes do disappear, and eventually disappear entirely, and with them goes the information used to build them. And this is where the blackbody radiation raised its head again. Hawking had discovered that this blackbody radiation emitted by black holes could not carry information with it. Hawking's calculations showed it was essentially random. If you monitored the particles and photons emitted by a decaying black hole, you could not discern the internal contents of what made the black hole in the first place. And so Bekenstein's no-hair theorem stayed correct. Once a black hole consumes something, we lose access to the information of what that thing was. But then the black hole disappears. What now? If the information didn't escape through Hawking radiation, then where did it go? This was the heart of the black hole information paradox, the seeming ability for black holes to swallow and destroy information, something that went against the hard laws of quantum mechanics. Information could never, ever be destroyed, and so Bekenstein and Hawking couldn't both be right. Either the radiation must carry away information with it, meaning Hawking was wrong about its nature, or black holes are hairy after all, and Bekenstein was incorrect.